Hey everyone, and welcome back for another deep dive. Today, we're tackling the density Hales-Jewett theorem,
Oh, wow.
specifically DHJ3.
Nice.
We've got this paper here claiming some pretty impressive improvements to the bounds for it.
Yeah.
And it
That's
gets
pretty intense.
pretty wild.
Yeah.
So we're going to explore not just what the theorem says,
All right.
but the why behind it, how it connects to other math problems.
Absolutely.
And we'll unpack the proofs step by step.
Yeah, this is exciting stuff because DHJK
Yeah,
is kind of like a cornerstone of combinatorics.
for sure.
You know, it has this ability to connect all these seemingly different problems together.
Yeah.
And DHJ3 is a particularly interesting case, I think.
Yeah. Okay, so let's start with a little bit of a recap.
Sure.
So DHJK basically says that if you have a large enough set of sequences,
Right.
with each sequence having K symbols,
Right.
and if that set is dense enough, you're guaranteed to find this special pattern,
Yes.
the combinatorial line.
A combinatorial line, exactly. So think of it this way.
Okay.
You have sequences of length in, right? And each position in the sequence can be one of different symbols,
Okay.
like 0, 1, 2, and so on.
Okay.
A combinatorial line is a set of K of these sequences,
Gotcha.
where each position either has the same symbol across all sequences, or it cycles through all the K symbols.
Okay, so like for DHJ3 with 3 symbols,
Yeah.
a combinatorial line could have all zeros in the first position, then all ones in the second,
You're right.
all twos in the third, and so on.
Exactly.
Or you could have another line with all ones in the first position,
Yeah.
then zeros and twos.
You got it.
You get the idea.
Yeah, the challenge with the DHJK is figuring out how W dense
Right?
your set of sequences needs to be to guarantee that such a line exists.
Yeah.
And that's where these bounds come in.
That's where these bounds come in, and that's where this paper is.
That's right.
Shaking things up.
Yeah.
Because previous proofs, even from the Polymath project, gave us these massive bounds talking about towers of exponent.
Bounds.
And this paper claims to have significantly lowered those bounds for DHJ3.
Yeah.
So what makes this a significant leap?
Well, the Polymath project, you know, while it was groundbreaking, it still required the sequence lengthen to be a tower of exponents
Okay.
with a height proportionate to the inverse density squared.
Wow.
This new paper shows that for DHJ3N only needs to be a tower of exponents of a fixed height.
Okay.
That's a big difference.
That's a huge difference.
Yeah, massive improvement.
Okay, so that's a breakthrough. So this
That-
paper's key result is laid out in Theorem 1,
Right.
which gives us this improved bound.
Yeah.
Basically, it says that if the density of your set A within the space of all possible sequences is greater than a certain value,
Okay.
which involves some, complicated logarithmic terms based on n,
Right.
then boom, you're guaranteed a combinatorial line of length 3.
You got it. And what's really cool is how this connects to other classic math problems.
Yeah.
Like take Semiretti's theorem, for example. It's about finding arithmetic progressions,
Yep.
sequences where each term increases by the same constant and
Yeah.
dense sets of integers.
Okay, so how does Semiretti's theorem relate to DHJK?
Well, there's this elegant encoding trick.
Okay.
You can encode each point in your DHJK set as a number
Uh-huh.
if you do this the right way.
Okay.
Finding a combinatorial line in your DHJK set
Yeah.
is equivalent to finding an arithmetic progression in the set of encoded numbers.
Whoa. So DHJK is like this master key that unlocks solutions to other problems.
That's a powerful tool.
That's so cool. And the paper mentions connections to the corners problem too, right?
Yes.
That's the one about finding right triangles in dense grids.
Exactly.
It makes me wonder if there are shared strategies in the proofs themselves.
It's definitely a web of interconnected ideas,
Yeah.
and this paper just adds another layer to that web.
For sure, the abstract really dives into the specifics.
Yes.
It essentially claims that within a specific set defined in the paper,
Right.
if you take a subset of a certain size,
Okay.
a size significantly smaller than what previous bounds required,
Yeah.
it has to contain a combinatorial line of length 3.
It has to.
So they're narrowing down the search space, tightening the net, so to speak.
Exactly.
I'm eager to see how they achieve this.
Me too.
The introduction seems like a good place to start unpacking the details.
Yeah, it's a great overview.
It mentions the van der Waerden theorem,
Right.
which states that any finite coloring of positive integers must contain a monochromatic arithmetic progression of any length.
And you know what's interesting?
What's that?
DHJK can actually be used to prove Semiretti's theorem,
Oh, wow.
which is basically the density version of van der Waerden's theorem.
Okay, yeah.
It's fascinating how these seemingly distinct concepts are so intertwined.
Yeah, and the introduction even lays out this encoding scheme you mentioned.
Right.
Showing how to turn a point in a DHJK set into a number, so that a combinatorial line directly maps to an arithmetic progression.
It's a really clever trick.
Yeah, it also connects DHJK to the corners problem.
Yes.
Demonstrating how finding those right triangles in a grid can be deduced from DHJK.
It even touches upon the multidimensional Semirati theorem.
Wow.
Hinting at the broad reach of DHJK in finding complex patterns within dense sets.
It seems like constraint satisfaction problems, or CSPs, play a role here as well.
They do.
I'm curious, how do CSPs factor into all of this?
Well, CSPs provide a powerful framework for studying relationships between variables.
Yeah.
You essentially have a set of variables and rules about how those variables can interact.
Yeah.
The goal is to find an assignment of values to the variables that satisfies all the rules.
So how are the authors using CSPs to tackle DHJ3?
It seems like a bit of a leap, right?
Yeah.
Well, they use CSPs to analyze the structure of functions that show strong correlations under specific probability distributions.
Okay.
And this allows them to leverage these powerful mathematical tools called inverse theorems. Oh, cool.
Which essentially tell you something about the structure of a function.
Okay.
Based on certain properties it displays.
Gotcha.
One example is the inverse theorem for the Gowers U2 norm.
Okay.
A measure of how random-like a function is.
This is where it gets really interesting.
It does.
Section 2 of the paper outlines their overall proof strategy.
Right.
And a key technique they use is called density increment.
Yes.
It's a common approach for these types of problems, right?
It is. The basic idea is to prove that either your set S contains the pattern you're looking for,
which is,
in our case, a combinatorial line,
right,
or it has even higher density within a smaller, more structured subset.
Okay.
Right.
So you keep iteratively zooming in on denser and denser substructures.
Exactly.
Until you either find the pattern or hit a contradiction.
You got it.
Proving that the pattern must exist in the original set.
It's a pretty clever strategy.
It's a really clever strategy, and the authors draw inspiration from Shkredov's proof.
Yes.
For the corners problem. That's right.
Where a similar density increment technique was used.
Mm-hmm.
Shkredov's approach relied on these things called combinatorial rectangles.
Right.
Subsets of the grid with specific properties.
Yeah.
And the process of finding denser substructures within them.
So in the corners problem, you have rectangles within a grid.
Right.
In DHJ3, the equivalent is something called disjoint products, right?
Okay.
Yeah.
So these disjoint products formed from sets that are sensitive to the symbol positions in your sequences.
That's right.
They play a similar role to the combinatorial rectangles.
Exactly.
Analyzing their structure is crucial for understanding when you can guarantee a combinatorial line.
It is. And for that, the authors introduce the concept of product pseudorandomness.
So is this our new definition of randomness for DHJ3?
You could say that product pseudorandomness, as defined in definition 3.1, is a stronger condition than the typical Fourier-based definitions.
Gotcha.
It captures a broader range of patterns and requires that even when you randomly fix some coordinates in your sequences, the resulting function doesn't strongly correlate with simple product functions.
So no matter how you slice it randomly, of course.
Right.
The function resists being explained by simple products.
Exactly.
That's pretty cool.
And what's really neat is that you can actually change the distribution against which you're testing for product pseudorandomness by strategically using random restrictions.
Interesting.
It's a way to tailor their analysis to the specific structure of the problem.
The random restrictions are like a multi-tool.
Yeah.
Helping them shape the analysis as needed.
That's a good way to put it.
It seems like the real power of product pseudorandomness comes from its connection to inverse theorems for CSPs, right?
Absolutely. You've hit the nail on the head.
Okay, awesome.
The authors leverage a significant generalization of the classic Gowers U2 norm inverse theorem, which they present as Theorem 2.
So just to remind ourselves about inverse theorems, they basically say that if a function has certain properties, it must have a particular underlying structure.
Precisely.
Right.
Theorem 2 specifically states that if you have three functions that are highly correlated under a pairwise connected distribution, then all three functions must lack product pseudorandomness.
So it's almost like saying that strong correlation implies a kind of structured non-randomness.
Right.
Seems counterintuitive at first.
It is a bit, but to relate it back to the familiar Gowers U2 norm, imagine applying this theorem to functions defined over an abelian group. The correlation condition would then mean that the Gowers U2 norm of one of the functions is large.
Okay.
Implying the function isn't pseudorandom in the usual Fourier analytic sense.
So they've taken this classic idea and extended it to work in a much more general setting.
Exactly. They've generalized it.
That's impressive.
It doesn't stop there. They go a step further and
yeah.
prove an inverse theorem for a specific type of Fourier distribution. That is a distribution over 4 tuples.
Okay.
This is Theorem 3 in the paper.
Why a 4-ary version?
Why is that necessary?
Yeah.
It's because of the structure of the DHJ3 problem itself.
Okay.
While they are ultimately interested in three-way correlations,
Right.
the analysis leads them to these 4-ary distributions,
Yeah.
which better capture the relationships between different parts of the combinatorial lines they're searching for.
I see. So it's like they need an extra dimension to fully grasp the complexity
That's a great way to put it.
of the problem.
Yeah, proving Theorem 3 directly would be quite messy.
Okay.
So they smartly reduce it to the 3-ary inverse theorem from Theorem 2.
Okay.
It's a bit analogous to how the Gowers U2 norm,
Yeah.
though defined over a 4-ary distribution, essentially has the same inverse structure as that for 3-term arithmetic progressions.
So they find the right level of abstraction to make the problem tractable.
Exactly. They simplify it.
Clever.
Yeah.
But how do they make this reduction work?
They do that by defining what it means for a distribution to be connected,
Okay.
which is laid out in definition 3.2.
Gotcha.
Essentially, you can move between any 2 points in the support of the distribution by changing one coordinate at a time, all while staying within the support.
So it's like navigating a network where you can travel between any 2 nodes by taking one step at a time.
Exactly.
Oh.
With this notion of connectedness, Theorem 3 basically says that if 4 functions show strong correlation under a Fourier distribution that has these specific connectivity properties, then at least one of those functions must lack product pseudorandomness.
Okay, so they've built up this impressive arsenal of inverse theorems.
Yeah.
Linking correlations to the absence of product pseudorandomness.
Right.
Yeah,
what
do they do with these powerful tools?
Well, that's where Section 4 inductive structure comes into play.
Okay.
They lay the groundwork for their density increment argument, which we'll dig into in the next section.
Let's jump into Section 4 then.
Let's do.
What are we dealing with here?
So they start by defining a measure on the space of all possible 3-symbol sequences.
Okay.
This isn't necessarily the uniform measure.
Gotcha.
They'll be working with several different measures throughout the proof.
Okay.
The key is that they need a way to quantify the density of combinatorial lines within a set.
That makes sense because they're building towards proving that a set with high enough density must contain a combinatorial line.
Exactly.
To do that, they need a way to measure that density.
Precisely. And then they introduce disjoint products of sets in definition 4.1.
Right.
This is essentially the counterpart to combinatorial rectangles in the corners problem.
Let me see if I've got this right.
Okay.
In the corners problem, we were searching for right triangles within a grid.
Yes.
Now in DHJ3, we're looking for combinatorial lines within the space of all possible 3-symbol sequences. These disjoint products take on a similar role to the rectangles.
You got it.
Okay, cool.
The disjoint product of 2 sets, say E1 and E2, is formed by taking all sequences where the positions corresponding to E1 satisfy certain properties, and the positions corresponding to E2 satisfy others.
Okay.
It's a way to create smaller, more structured subsets within the larger space of sequences.
I'm curious, why is this construction so important?
What purpose do these disjoint products serve?
Yeah.
They're crucial for the density increment argument.
Okay.
The idea is to begin with a set S that's dense within the disjoint product of some sets E1 and E2.
Okay.
Then they prove that if S doesn't contain a combinatorial line, it must be even denser within the disjoint product of some smaller sets, E1 prime and E2 prime.
So it's like a process of repeatedly focusing on the densest regions.
Exactly.
Zooming in further.
The key aspect of making this work is ensuring that E1 and E2 are product pseudorandom.
Right.
That's where lemma 4.3 comes in. It establishes a connection between the product pseudorandomness of E1 and E2 and the measure of their disjoint product.
So if E1 and E2 are product pseudorandom enough, the measure of their disjoint product is roughly what you'd expect.
Right.
If being in E1 and being in E2 were independent events.
Precisely.
Okay.
Product pseudorandomness gives them control over how these disjoint products behave.
Yeah.
which is essential for their density increment argument.
For sure. And with that, they've set the stage for the most critical part of the proof.
Yes, they have.
Which we'll tackle in the next section.
Sounds good.
This is getting really exciting, but I think we should pause here for now.
Okay.
And give our listeners a chance to digest everything.
Sure.
We'll be back soon with part 2 of this deep dive.
Okay.
Where we'll explore the culmination of all these ideas.
Looking forward to it. Welcome back to our deep dive into the density Hales-Jewett theorem and this groundbreaking paper.
I'm ready to dig in.
Yeah, let's pick up where we left off and really get into the heart of this paper's argument. Starting with section 3, which focuses on correlations to product functions.
Okay, I'm ready to get into the nitty-gritty of product pseudorandomness.
Yeah.
This feels like a core concept in their approach.
You're absolutely right. The section starts by formally defining product pseudorandomness.
Okay.
Remember, a function is considered product pseudorandom if even after you randomly restrict it to a subset of coordinates, it's still unlikely to strongly correlate with simple product functions.
So no matter how you slice it randomly, of course, the function resists being explained by simple products.
Exactly.
That's pretty interesting.
And the authors point out that you can actually change the distribution against which you're testing for product pseudorandomness by strategically using random restrictions.
Interesting.
It's a way to tailor their analysis to the specific structure of the problem.
So random restrictions are like a multi-tool, helping them shape the analysis as needed.
Yeah, that's a good analogy.
It seems like the real power of product pseudorandomness comes from its connection to inverse theorems for CSPs, right?
You've hit the nail on the head. The authors leverage a significant generalization of the classic Gowers U2 norm inverse theorem, which they present as Theorem 2.
So just to remind ourselves about inverse theorems, they basically say that if a function has certain properties, it must have a particular underlying structure.
Precisely.
Right.
Theorem 2 specifically states that if you have 3 functions that are highly correlated under a pairwise connected distribution, then all 3 functions must T lack product pseudorandomness.
It's almost like saying that strong correlation implies a kind of structured non-randomness.
Right.
It seems counterintuitive at first.
It is a bit, but to relate it back to the familiar Gowers U2 norm, imagine applying this theorem to functions defined over an abelian group. The correlation condition would then mean that the Gowers U2 norm of one of the functions is large, implying the function isn't pseudorandom in the usual Fourier analytic sense.
So they've taken this classic idea and extended it to work in a much more general setting.
Exactly. They've generalized it.
That's impressive.
It doesn't stop there. They go a step further.
Oh, wow.
And prove an inverse theorem for a specific type of Fourier distribution.
Okay.
That is a distribution over 4 tuples.
Okay.
This is Theorem 3 in the paper.
Why a Fourier reversion? Why is that necessary?
Well, it's because of the structure of the DHJ3 problem itself.
Okay.
While they are ultimately interested in 3-way correlations, the analysis leads them to these Fourier distributions, which better capture the relationships between different parts of the combinatorial lines they're searching for.
I see. So it's like they need an extra dimension to fully grasp the complexity of the problem.
That's a great way to put it.
Yeah.
Proving Theorem 3 directly would be quite messy.
Okay.
So they smartly reduce it to the 3-area inverse theorem from Theorem 2.
Okay.
It's a bit analogous to how the Gowers U2 norm, though defined over a 4-itery distribution, essentially has the same inverse structure as that for 3-term arithmetic progressions.
So they find the right level of abstraction to make the problem tractable.
Exactly. They simplify it.
Clever. But how do they make this reduction work?
They do that by defining what it means for a distribution to be connected.
Okay.
Which is laid out in definition 3.2.
Gotcha.
Essentially, you can move between any 2 points in the support of the distribution.
Okay.
By changing one coordinate at a time, all while staying within the support.
So it's like navigating a network where you can travel between any 2 nodes by taking one step at a time.
Exactly. With this notion of connectedness, Theorem 3 basically says that if 4 functions show strong correlation under a 4-arity distribution that has these specific connectivity properties, then at least one of those functions must lack product pseudorandomness.
Okay, so they've built up this impressive arsenal of inverse theorems linking correlations to the absence of product pseudorandomness. What do they do with these powerful tools?
Well, that's where section 4 inductive structure comes into play.
Okay.
They lay the groundwork for their density increment argument, which we'll dig into in the next section.
Let's jump into section 4 then. What are we dealing with here?
So they start by defining a measure on the space of all possible three-symbol sequences.
Okay.
This isn't necessarily the uniform measure.
Gotcha.
They'll be working with several different measures throughout the proof.
Oh, okay.
The key is that they need a way to quantify the density of combinatorial lines within a set.
That makes sense. Because they're building towards proving that a set with high enough density must contain a combinatorial line.
Yes.
To do that,
yes,
they need a way to measure that density.
Precisely. And then they introduce disjoint products of sets in definition 4.1.
Okay.
This is essentially the counterpart to combinatorial rectangles in the corners problem.
Let me see if I got this right. In the corners problem, we were searching for right triangles within a grid.
Yes.
Now in DHJ3, we're looking for combinatorial lines within the space of all possible three-symbol sequences. These disjoint products take on a similar role to the rectangles.
You got it. The disjoint product of two sets, say E1 and E2, is formed by taking all sequences where the positions corresponding to E1 satisfy certain properties, and the positions corresponding to E2 satisfy others.
Okay.
It's a way to create smaller, more structured subsets within the larger space of sequences.
I'm curious, why is this construction so important? What purpose do these disjoint products serve?
They're crucial for the density increment argument. The idea is to begin with a set S that's dense within the disjoint product of some sets E1 and E2.
Okay.
Then they prove that if S doesn't contain a combinatorial line, it must be even denser within the disjoint product of some smaller sets, E1 prime and E2 prime.
So it's like a process of repeatedly focusing on the densest regions, zooming in further and further.
Exactly. A key aspect of making this work is ensuring that E1 and E2 are product pseudorandom.
Right.
That's where lemma 4.3 comes in. It establishes a connection between the product pseudorandomness of E1 and E2 and the measure of their disjoint product.
So if E1 and E2 are product pseudorandom enough, the measure of their disjoint product is roughly what you'd expect if being in E1 and being in E2 were independent events.
Precisely. Product pseudorandomness gives them control over how these disjoint products behave.
Yeah.
Which is essential for their density increment argument. And with that, they've set the stage for the most critical part of the proof, which we'll tackle in the next section.
This is getting really exciting. But I think we should pause here for now and give our listeners a chance to digest everything. We'll be back soon with part 3 of this deep dive, where we'll explore the culmination of all these ideas. Welcome back, everyone. We're in the home stretch of our density Hales-Jewett deep dive, and I'm really excited to see how all these intricate pieces come together.
It's definitely an impressive mathematical tapestry they've woven. We left off on the brink of their density increment argument. Section 5, titled Moving Between Measures, lays the groundwork for establishing a crucial three-way correlation.
Right. We need to connect the absence of combinatorial lines to these specific correlations they've been developing.
Yeah.
This seems like a pivotal step.
Absolutely. One of the main challenges here is finding the right measure for counting combinatorial lines. They construct a very specific distribution called D in definition 5.1, which involves a sequence of carefully designed perturbations to the uniform distribution.
So instead of just assuming every sequence is equally likely, they're slightly tweaking the probabilities. It's like they're fine-tuning their lens to better spot the patterns they're after.
Exactly. And lemma 5.2 showcases the power of this approach. It demonstrates that under this new distribution D, there's a pair of sequences with a correlation significantly higher than you'd expect if they were truly random.
It's like they're amplifying a faint signal, making it easier to detect.
Yeah.
But how does this relate back to combinatorial lines?
That's where lemma 5.3 comes in. It proves that if a set S, which lies within a specific structure defined as struct S in the paper, contains NO combinatorial lines, then a particular three-way correlation involving the indicator function of S must be large. This is a critical turning point because it sets the stage for the density increment argument.
Okay, so now they've linked the absence of combinatorial lines to a specific type of correlation. I'm ready to see how they use this to actually increase the density. What happens next?
In section 5.2, they introduce a technique called harsh random restrictions. This involves fixing a large number of coordinates in your sequences to specific values. Lemma 5.5 shows that even after applying these harsh restrictions, product pseudorandomness is preserved.
So it's like saying even after simplifying the function significantly, it retains this special type of randomness. Why is this important?
It's crucial because they'll be working with many different distributions throughout the proof. By showing that harsh restrictions preserve product pseudorandomness across various distributions, they streamline their analysis.
I'm starting to see how all these pieces fit together. What about this set Q they define in definition 5.6? What's its purpose?
Q is essentially their toolkit of distributions. It includes a wide range of distributions with rational probabilities, which makes the analysis more manageable. Lemma 5.7 takes the correlation from Lemma 5.3, applies harsh random restrictions, and then establishes a similar correlation under a distribution from Q, where all probabilities are bounded away from zero. This is key because certain inverse theorems require this property.
It feels like they're carefully setting the stage for the grand finale, their density increment argument.
You're exactly right. Section 6, aptly titled Density Increment, dives right into the heart of it. Theorem 4 utilizes a series of Cauchy-Schwarz inequalities to link the three-way correlation from Section 5 to something called the box norm.
I'm intrigued. What exactly is the box norm?
It's a measure of how unevenly a function is distributed within specific subsets. In this case, the box norm inequality suggests that if S doesn't contain combinatorial lines, then there must be denser substructures within S.
So it's another way to capture this idea that S has to exhibit some non-random structure if it's avoiding these patterns, like they're cornering it, forcing it to reveal its secrets.
Precisely. To bolster Theorem 4, they proved two technical lemmas, lemmas 6.1 and 6.2, which use product pseudo-randomness to bound certain expectations.
It's amazing how they managed to weave all these complex tools together into a coherent argument.
It's a testament to their mathematical ingenuity. Theorem 5 then combines random restrictions and the box norm inequality to actually locate a denser substructure S prime within a smaller dimensional space. This is the core of their density increment strategy.
So if there's no combinatorial line in S, there has to be a region where the density is even higher. It's like they're closing in on the hiding place of that combinatorial line.
That's a great way to visualize it.
Yeah.
Now we come to Section 7, uniformization, which tackles the challenge of ensuring that the sets E1 and E2 are product pseudo-random enough for the density increment argument to work smoothly.
So after finding S prime, they need to ensure they're still working with a nice product pseudo-random environment. What's their strategy?
Theorem 6 is their key weapon here. It guarantees that they can always find a uniformized structure that is sets E1 prime and E2 prime that are product pseudo-random without losing too much density in the process.
So they're refining the sets, making them more suitable for analysis without sacrificing the density they've worked so hard to build up.
Exactly. They achieve this by combining two types of random restrictions: the standard type and a special type that forces certain coordinates to have the same value. Lemma 7.1, a crucial technical result, shows how to implement this partitioning process, iteratively increasing a distributions index until it converges to a uniformized structure.
There's a remarkable dance of techniques, all carefully coordinated to achieve their goal.
Wow.
So how does this all lead to the proof of Theorem 1?
The final proof of Theorem 1 outlines the iterative process of applying the density increment from Theorem 5 and the uniformization from Theorem 6. By carefully choosing their initial parameters, they ensure this process eventually terminates before the dimension shrinks too much. At that point, a combinatorial line must exist.
Wow, we've covered a lot of ground. It's been a truly intense journey through some very advanced mathematics.
It certainly has. This paper is a significant achievement. Not only does it offer greatly improved bounds for DHJ3, but it also introduces powerful new techniques, particularly this concept of product pseudo-randomness, which could have far-reaching implications for other problems in combinatorics.
I'm still marveling at how they managed to connect so many different ideas. Samoraity's theorem, the corners problem, CSPs, inverse theorems, and this clever use of random restrictions. It's a beautiful symphony of mathematics.
Absolutely. And it leaves us with a tantalizing question. Could this approach, with its emphasis on product pseudo-randomness, pave the way for even better bounds for DHJK when Co is larger than 3?
That's a fantastic question. It seems like there's still so much to explore in this fascinating area of mathematics. For now, though, I think we've earned a break after this incredible deep dive.
I wholeheartedly agree. Until next time, keep those mathematical minds engaged and stay curious.
Welcome to another deep dive. Today we're going exploring the world of extremal combinatorics with a paper called Reasonable Bounds for Combinatorial Lines of Length 3.
Yeah, this paper's a real gem, even if it is a bit dense.
It is dense, but that's why we're here, to break it down together.
Exactly. It's all about finding those aha moments hidden in the math.
So we're dealing with this thing called the density Hales-Jewett theorem.
DHJ for short.
DHJ for short, right? And this paper focuses on DHJ3, which I guess means finding these combinatorial lines of length 3.
You got it. And it all takes place within these special sets.
Can you unpack that a bit?
Yeah.
What exactly is a combinatorial line, and what kind of sets are we talking about?
Sure. Imagine a set of points, but instead of just being on a line, they're in a multi-dimensional space.
Okay, so each point has multiple coordinates.
Yeah, like 0, 1, 2. Now, a combinatorial line of length 3 would be 3 points in this set where
they all line up somehow.
Not quite lining up, but there's a pattern. The values at a specific coordinate either have to be all the same or follow an arithmetic progression, like 0, 1, 2.
I think I'm starting to see it. So if we had points like 0, 0, 0, 0, 1, 1, 1, 1, and 2, 2, 2, 2, that would be a combinatorial line.
Perfect example, because they all follow that 0, 1, 1, 2 pattern.
Okay, that makes sense. So DHJ3 is trying to figure out how dense a subset of a larger set needs to be to guarantee that we'll find at least one of these lines.
Exactly. The larger set is denoted as 3n, which basically means all possible combinations of 0s, 1s, and 2s in strings of length n.
And n can be any number, right? So these sets can get pretty massive.
Oh, absolutely. They can get incredibly huge, which is why finding those lines isn't always easy.
And that's where this paper comes in with its improved bounds, right?
Right. What this paper does is it takes those previously known bounds, which often involve these towering exponents.
Powers, like those math problems that go to the power of 2, to the power of 2, and so on.
Exactly. Those towers could get ridiculously tall, like with heights of O2, where Aki represents the density.
Ouch, my brain hurts just thinking about that.
Yeah, they were hard to even wrap your head around. But what's remarkable is this paper manages to bring those tower heights down to a fixed number for DHJ3.
So no more ridiculously tall towers. That's got to be a big deal for anyone working in this field.
It's huge GE. It means those combinatorial lines are easier to find than we initially thought.
This feels like more than just a refinement of the bounds. It's a fundamental shift in our understanding of how these lines behave.
Couldn't have said it better myself. And to do this, the authors bring together all sorts of cool mathematical concepts.
I noticed they connected DHJ3 to things like Semiretti's theorem and the corners problem, which seemed completely unrelated at first glance.
Yeah, those connections were pretty mind-blowing. Semiretti's theorem deals with arithmetic progressions in sets of numbers.
Okay, and DHJ3 deals with patterns in sets of points.
Right, but the paper cleverly shows how you can translate those points into numbers.
How do they do that?
Think of each coordinate in a point as a digit in a base 3 number system.
So our example from before, 0, 0, 1, 1, 1, 2, 2, those become 0, 1, and 2 in base 3.
Exactly. And now a combinatorial line becomes an arithmetic progression.
Wow, that's elegant. So they're finding hidden arithmetic progressions within these seemingly random sets of points.
Precisely. And that's the bridge that connects DHJ3 to Semiretti's theorem.
And what about the corners problem? How does that fit into this web of connections?
The corners problem is about finding specific triangles and grids of points, but it turns out you can view it through the lens of DHJ as well.
Really? I'm starting to see DHJ3 as this sort of Rosetta Stone, unlocking secrets across different areas of math.
I like that analogy. It's like a fundamental building block for understanding these complex patterns.
And this paper strengthens that building block, giving us a firmer foundation to build upon.
Absolutely. And they don't stop there. They even venture into the world of computer science with something called constraint satisfaction problems, or CSPs.
I was wondering about that. CSPs are used in all sorts of algorithms and AI applications, right?
You got it. And the authors show how DHJ3 can actually be framed as a CSP.
So finding those combinatorial lines becomes like solving a constraint puzzle.
You could think of it that way. It's another unexpected connection, bridging the gap between pure math and computer science.
My mind is officially blown. But before we dive into the details of their approach, I'm curious about one thing. What's the secret sauce that allows them to achieve these improved bounds?
Their secret weapon is something called product pseudorandomness.
I remember seeing that term in the paper, but I'm not sure I fully grasped it. What does it mean, and why is it so important?
Imagine you want to test how random something is. You might check if it correlates with simple patterns.
Like seeing if a sequence of numbers is evenly distributed or if it clumps together.
Exactly. Product pseudorandomness takes this further. It checks for correlations with products of those simple patterns.
So it's like checking for randomness on a whole other level, a much more sophisticated test.
Precisely. And it's this extra level of scrutiny that unlocks those improved bounds for DHJ3.
It allows them to see deeper into the structure of those sets.
Exactly. They can spot subtle patterns and relationships that were previously hidden, which is key to their whole strategy.
Okay, we've got this powerful new tool, connections to other problems, and a framework borrowed from computer science. I'm dying to know, how do they put it all together in their proof?
Well, Section 2 lays out their game plan, and it's pretty ingenious. They combine three main ingredients: a specific way of measuring those combinatorial lines, some cleverly chosen sets called O2 insensitive and O1 insensitive sets, and of course their product pseudorandomness.
Let's break that down a bit. What's the special way of measuring the lines?
It's called the equal slices measure. Think of it like a ruler that's designed specifically to detect those combinatorial patterns.
Okay, so we have our measuring tool. What about those insensitive sets? What do they do?
They're a bit like those combinatorial rectangles you find in the corners problem. They have a specific structure that the authors can exploit.
Like a framework that helps them organize the problem.
Exactly. And then they use product pseudorandomness for something called uniformization.
Uniformization? What's that?
It's like taking something rough and uneven and smoothing it out. By uniformizing those sets, they can then apply their density increment strategy, which is the heart of their proof.
Density increment? That sounds intriguing.
Basically, it involves refining those sets repeatedly, making them denser and denser with those combinatorial lines.
Like squeezing them out.
Exactly. And to achieve this, they introduce a whole bunch of lemmas and theorems in sections 5 and 6, building their argument step by step.
Okay, I'm sensing this is where things start to get really intricate.
It does get pretty technical, but each step builds on the previous one, like a carefully constructed puzzle.
Well, I'm ready to tackle that puzzle, but I think we'll save that for the next part of our deep dive.
Sounds like a plan. There's a lot more to uncover as we journey deeper into this remarkable paper.
Welcome back to our deep dive. We left off with the promise of a density increment strategy, ready to squeeze out those combinatorial lines. It all feels like we're about to witness a mathematical magic trick.
It's more like a carefully choreographed dance where each move leads to the next. And a key part of that choreography is the uniformization process.
Right, the smoothing out step. Section 7 really gets into the nitty-gritty of how they do that.
Exactly. It all hinges on Theorem 6, their tool for reshaping those sets and making them exhibit product pseudorandomness.
It's like giving those sets a makeover, getting them ready for the main event. But the proof of Theorem 6, I have to admit, that one was a bit of a head-scratcher.
It is pretty intricate. They actually adapt a technique from Shkridov's proof of the corners problem.
Wait, the corners problem? I thought that was a completely different beast.
It does seem unrelated at first glance, but the authors find this clever way to connect them. Their adaptation involves this special operation where they force a subset of coordinates to have the same value.
So they're introducing a new constraint to simplify the problem.
You could say that. It's like taking a bunch of loose threads and tying them together neatly.
But how do they make sure that this tying doesn't mess up the properties they need for their proof?
That's where lemma 7.3 comes in. It's a crucial piece that shows this operation doesn't disrupt those statistical properties, especially those related to product pseudorandomness.
So it's a delicate balancing act, making changes without upsetting the whole system.
Exactly. And this allows them to use lemma 7.1 repeatedly.
Which does what, exactly?
Lemma 7.1 uses this tying operation to gradually increase a measure called the index.
The index. That's a way of measuring how spread out the sets are, right?
Precisely.
Right.
By increasing the index, they essentially force the sets to become less spread out, more concentrated.
So they're herding those combinatorial lines together, making them easier to catch.
Great analogy. And they keep herding until those sets exhibit the desired level of product pseudorandomness. They become uniformized.
Like training those sheep to move in perfect unison. And once they achieve this uniformity, they can finally bring in Theorem 5, their density increment weapon.
You got it. They've set the stage, and now the real action begins.
So how does this density increment actually play out in the proof of Theorem 1?
It's an iterative process. They show that by repeatedly applying Theorems 5 and 6, they can keep increasing the density of those lines within the sets.
Step by step, tightening the net until there's nowhere for those lines to hide.
Precisely. And what's really cool is that they meticulously track the density and dimension of those sets as they go through this process.
Why is that important?
They have to maintain a delicate balance. The density needs to keep increasing, but the dimension can't shrink too much. It's like navigating a ship through a narrow channel, making sure it doesn't run aground.
Sounds like a tricky maneuver.
It is. They need to find that sweet spot where those combinatorial lines are guaranteed to exist.
And they prove that their method actually reaches this sweet spot.
They do. Through a series of careful calculations and inequalities, they show that starting with a sufficiently large set and applying their method guarantees the appearance of those combinatorial lines. It's not just luck, it's meticulous planning and execution.
So they've essentially engineered a mathematical trap, and those lines can't escape. It's pretty amazing what they've accomplished.
It really is. They haven't just stumbled upon a result. They've developed a robust method, a foolproof recipe for finding those combinatorial lines.
This feels like a major step forward in the field. What kind of impact do you think this work will have?
Well, the improved bound for DHJ3 is a significant advancement, for sure. But it's more than that. It shows the power of new tools like product pseudorandomness and highlights the surprising connections between different areas of math.
It's like they've given us a new map, revealing hidden pathways and relationships.
Exactly. And who knows what other treasures await us as we explore these new territories.
This paper has certainly sparked my curiosity. I'm eager to see where this line of research leads next.
Me too. It's a testament to the power of human ingenuity, the creativity and persistence that drives mathematical progress.
And on that note, I think we're ready for the final part of our deep dive, where we can reflect on the broader significance of this work and what it might hold for the future.
Let's dive in.
Welcome back to the deep dive. It's been quite a journey through the world of combinatorial lines, density theorems, and even a detour into computer science.
It has been. And now, as we wrap up, it's time to zoom out and look at the bigger picture.
Exactly. Why should all this matter to mathematicians, computer scientists, or even anyone outside those fields?
Well, on a practical level, we now have a much better understanding of DHJ3.
Because those lines are easier to find than we thought.
Exactly. We can guarantee their existence in less dense sets, which changes how we approach problems in this area.
It's not just a theoretical curiosity. It has real-world implications.
Precisely. And it all comes down to those innovative tools and approaches, like product pseudorandomness.
That really was the key, wasn't it? It allowed them to see those sets in a whole new light, revealing hidden structures.
It's like they had a superpower, allowing them to manipulate those sets with incredible precision.
Smoothing them out, concentrating them, and ultimately forcing those lines to appear.
It's a beautiful example of how the right tools can lead to breakthroughs. But beyond the technical achievements, there's something even more profound here.
You mean those connections they made, right? Linking DHJ3 to Simorades theorem and the corners problem?
Exactly. It shows how interconnected math really is, how seemingly unrelated areas can share deep underlying principles.
It's like exploring a vast interconnected network, full of hidden pathways and surprises.
And that's what makes research so exciting. You never know what you'll find when you start digging.
And we can't forget that bridge to constraint satisfaction problems.
That connection opens up a whole new avenue for exploration, a dialogue between pure math and computer science.
What kinds of possibilities do you see emerging from that?
Who knows? Maybe we'll see insights from computer science applied to other problems in combinatorics, or new algorithms inspired by these theoretical results.
It's a wide-open field, full of potential.
And that's the message I hope our listeners take away from this deep dive. A sense of wonder, an appreciation for the interconnectedness of knowledge, and the understanding that even the most abstract math can have unexpected implications.
This paper is a testament to the power of human curiosity, the drive to explore and push the boundaries of what we know.
And it's a reminder that there's always more to learn, more connections to uncover, more mysteries to solve.
It's been a real pleasure exploring this fascinating paper with you. I hope our listeners have enjoyed the journey as well.
Me too. And remember, keep asking questions, keep exploring, and keep pushing the boundaries of knowledge.
Welcome back, everyone. Ready for another deep dive? Today, we're going to untangle a pretty fascinating concept in Ramsey theory, the density Hales-Jewett theorem.
Ah, yes. The DHJ theorem. Always a fun one. It really gets to the heart of how patterns inevitably emerge in large sets, even when they seem random.
Exactly. And we've got this paper here that tackles a specific piece of it, DHJ3, which, if I understand correctly, is all about finding lines, combinatorial lines, that is, of length 3 within a cube made up of zeros, ones, and twos.
You got it. Think of it like we have this cube, right?
Right.
And each corner is a unique combination of those three numbers. DHJ3 is about finding special lines within those combinations.
Okay, I think I can picture that. So is this paper offering a new proof for DHJ3?
It is, and it's a much more efficient proof than what we've had before. Previous solutions were incredibly complex, involving these massive calculations with towers of exponents. This paper streamlines things significantly.
I can imagine. Anything that simplifies those exponential towers has got to be a win. So why is DHJ3 so important? It seems pretty specific, focusing just on lines of length 3.
It might seem that way, but DHJ3 is kind of like a foundational case. You know, like mastering the basics before you can build something more complex. Understanding it lays the groundwork for tackling more general patterns.
Ah, so it's like a key that unlocks a whole set of doors to understanding broader patterns.
Precisely. And the main result of this paper, what they call Theorem 1, states that any subset of this cube, which they denote as 3n, if it's dense enough, it has to contain a combinatorial line of length 3.
Dense enough.
Yeah.
Meaning it has to have a certain number of elements packed into it.
Exactly. And the paper actually gives a more precise definition for that threshold of density than previous work. It's like they've drawn a tighter boundary around what dense enough really means. Before, the threshold was defined by a tower function with height O, where O is the density of the subset.
Okay, you're going to have to remind me what those tower functions look like again.
Oh, right. Think of it as repeated exponentiation. Like you're building a tower where each level is an exponent on top of the one below it. It gets huge really quickly.
Yeah, I'm starting to remember those now. Not exactly friendly to work with. So is this paper saying they've found a simpler way to express that threshold?
Yes, and that makes it much more manageable to work with.
That's a huge step. So we've got our cube, our lines of length 3, and a better definition of density. Where do we go from here? What other mathematical concepts does this theorem tie into?
Well, there are some really fascinating connections. For instance, think about van der Waerden's theorem. Have you heard of it?
Vaguely. It rings a bell.
Yeah.
Something to do with sequences, right?
You got it. It's about finding arithmetic progressions in large enough sets, basically sequences of numbers where the difference between each number is constant.
Ah, okay. So both DHJ3 and van der Waerden's theorem are looking for specific patterns in sets, even if those sets look random at first glance.
Exactly. And then there's Semerati's theorem, which is like a turbocharged version of van der Waerden's theorem. It applies to even more complex patterns within these dense subsets.
Wow, so DHA3 is like a piece of this larger puzzle, a puzzle that connects all these different areas of mathematics.
It is. And it doesn't stop there. This paper even draws a parallel between DHJ3 and something called the corners problem.
Corners, as in corners of a shape.
You could think of it that way. It involves finding right triangles within grids of numbers.
Okay, triangles, grids. I'm trying to picture how this relates to our cube and those lines of length 3.
The connection is more about the techniques used to solve them. The paper draws inspiration from a specific approach used to tackle the corners problem, called the density increment method. It was developed by a mathematician named Shkredov.
So mathematicians are borrowing techniques from one area of math to solve problems in another. It's pretty cool.
Yeah.
Tell me more about this density increment method.
Well, Shkredov's approach starts by assuming there are NO corners in a sufficiently dense subset.
Wait, so you start the proof by assuming the opposite of what you're trying to prove.
Exactly. It might sound counterintuitive, but it's a powerful technique. By assuming no corners exist, he was able to show that the density of corners must increase on a smaller, more structured subset.
It's like you're zooming in on a particular region of the grid, right? And by doing that, you're forcing those corners to become more and more likely.
Exactly. And you can repeat the zooming in process over and over. Eventually, you reach a point where the density is so high that the existence of corners becomes undeniable, contradicting your initial assumption.
Ah, a proof by contradiction.
Yeah.
Clever. But how does this all relate to DHJ3? We're not dealing with corners in a grid, we have lines in a cube.
You're right. The paper takes this idea of density increment and cleverly adapts it to the world of DHJ3. So instead of corners, we have these special lines. And instead of zooming in on specific regions of a grid, we're working with carefully constructed subsets within our cube of combination.
So it's like taking the blueprint of that corners proof and modifying it to fit the DHJ3 puzzle.
You got it. But of course, there are some unique challenges in making that leap.
I bet. It seems like there would have to be. What kind of challenges?
Well, for one, measuring combinatorial lines is a bit trickier than counting corners in a grid. You need a clever way to define how you're quantifying these lines within the sets.
It's like you need a special set of measuring tools just for this task.
Precisely. And then, even though we have these carefully constructed subsets to work with, we need some new concepts to really make this density increment strategy work. The paper introduces the idea of what they call O2 insensitive and O1 insensitive sets, and this thing called their disjoint product.
Okay, those are some new terms for me.
Yeah.
What are O2 insensitive and O1 insensitive sets? And what's this disjoint product all about?
Okay, imagine looking at our cube of combinations and just focusing on where the ones are. A O2 insensitive set is a subset where membership is determined only by those ones. Like you ignore everything else and just look at how the ones are arranged.
So it's like a filter highlighting specific combinations based on where the ones are. And what about EO1 insensitive sets?
Same idea, but focusing on the twos instead.
Okay, I think I'm following. But what about this disjoint product you mentioned? How does that fit in?
The disjoint product of a O2 insensitive set and an O1 insensitive set that acts kind of like those zoomed-in regions in Skradov's corners proof. It gives you a smaller, more structured subset within the cube where those lines are more likely to appear.
It's like creating a custom-made search area within our cube, tailored for finding these lines.
Exactly. And there's one more really important concept we need to talk about before we dive deeper into the proof product pseudorandomness.
Okay, pseudorandomness. I know randomness, but what makes it product pseudorandomness?
It basically means that the sets behave the way we would expect truly random sets to behave. It's like setting a high bar for randomness to ensure that our analysis is robust.
So it's not just any randomness, it's a very specific type of randomness that's crucial for this proof to work.
Yes. It helps us control how things change when we apply those random restrictions we were talking about before, like slicing up our cube into smaller pieces.
Ah, right, like making sure our mathematical tools still work even when we're zooming in on those smaller sections.
Exactly. So to recap, we're borrowing the density increment concept from Skradov's work on corners, adapting it to DHJ3 using these new ideas of O2 insensitive and O1 insensitive sets and their disjoint product, and then we're relying on this concept of product pseudorandomness to make sure our analysis is solid.
Wow, it's like a whole symphony of mathematical ideas coming together.
I like that. And we're just getting started.
I can't wait to see how it all plays out.
So the proof of Theorem 1, it's structured really carefully, kind of like a well-composed piece of music. Each part builds on the one before it. And the first step, you need to pick the right tool to measure those combinatorial lines within our subsets.
So we need a way to quantify those lines, like finding the right unit of measurement.
Yeah, exactly. A measure that really captures the essence of what we're looking for. Once we have that, we can figure out the expected number of lines we should find if things were totally random. Kind of sets a baseline for comparison.
So we're establishing what's normal, what we'd expect to see just by chance, before we start looking for those special lines.
Precisely. And now we get to a crucial part, understanding how this measure and that whole product pseudorandomness thing, how they behave when we apply random restrictions.
Right. Those slices of the cube we talked about before. We're shrinking the space, so we need to make sure our tools still work.
Exactly. And that brings us to the heart of the proof, the density increment technique.
Ah, yes. Back to Skradov and the corners problem. How does that technique get applied to DHJ3?
It involves a few clever steps. First, we use something called the Cauchy-Schwarz inequality to get this thing called a large box norm. Think of the box norm as a way to measure how concentrated our set is within certain parts of our combination space.
Cauchy-Schwarz. That wouldn't spell like from calculus class. But how does it apply here?
The Cauchy-Schwarz inequality. It's really powerful for working with averages and figuring out bounds. It lets us quantify how tightly packed things are.
Okay, so if we have a large box norm, that means our set is really dense in certain regions.
You got it. And once we have this large box norm, we can use random restrictions, like we talked about, those slices, to force the density to increase even more on a smaller, structured subset.
So by shrinking the space, we're making it more likely to find those lines because everything's packed in tighter.
Precisely. And that whole product pseudorandomness thing we talked about, that ensures that this density increase happens in a predictable way.
It's like that product pseudorandomness is guiding the process, making sure the density increase doesn't go off the rails or something.
You could think of it that way. And there's one more key step in this proof-forcive. Something called uniformization. Remember how our sets might not always have that perfect product pseudorandomness? Well, uniformization is all about smoothing things out, making them behave better.
So it's like taking something that's messy and making it more organized, more predictable.
Yeah. We want those sets to behave nicely, so our analysis works smoothly. And uniformization involves breaking down our sets into smaller pieces until they do have that product pseudorandomness.
Okay, so we're partitioning the sets to achieve that desired level of randomness. But how do we actually do that partitioning? What's the process?
The paper uses two types of random restrictions to do this. First, we've got those standard restrictions we talked about, where you fix the values of some coordinates randomly, remember, like those slices we talked about. But then they also introduce a second type, where you actually force certain coordinates to have the same value.
Oh, interesting. So two types of restrictions working together. But why do we need both types? Wouldn't one be enough?
They kind of work in tandem. The standard restrictions help create those smaller, focused subsets. And then the second type, by forcing some coordinates to be the same, it introduces this really subtle control over the structure of our sets. It's kind of hard to explain without getting too deep in the weeds.
No worries. I think I get the general idea. We're using these two types of restrictions to achieve that balance, creating uniformity without sacrificing too much density.
Exactly. It's pretty amazing how they managed to do it. Are you ready to see how all of this comes together in the proof of Theorem 1?
You bet. Let's hear it.
So we've laid out all the pieces: density increment, uniformization, these special sets, and the paper ties it all together beautifully to show how those combinatorial lines have EE to exist. We start with this simple structure, right? And then we just keep applying those density increments and uniformization steps over and over.
Each step pushing the density higher and higher, like we're building up to something.
Yeah, exactly. And as the density increases, eventually we hit this point where if we were to assume that there are NO combinatorial lines, well, we run into a problem, a contradiction.
So we're assuming the opposite of what we want to prove and showing that it leads to something impossible.
Exactly. It's a classic proof by contradiction. The density gets so high that it breaks the rules, so to speak. You can't pack that much stuff into the subset without those lines appearing.
It's like trying to fit a square peg in a round hole.
Yeah.
Eventually, something's got to give. So by showing that our initial assumption that there are NO lines leads to an impossible scenario, we prove that those lines must exist.
Exactly. That's the beauty of this paper. It's not just about finding a needle in a haystack. It's about proving that the haystack itself is structured in a way that guarantees those needles are in there somewhere.
I love that. So weaving together density increments, uniformization, and that clever proof by contradiction, we get this really powerful result that any sufficiently dense subset within our cube has to contain those special lines.
That's it. That's the core of the paper.
This has been an amazing journey. What are some of the key takeaways you think our listeners should hold on to? What really struck you about this paper?
I think the biggest thing for me is how the paper connects all these different ideas from different areas of math. Corners, those constraint satisfaction problems, pseudo-randomness.
Yeah.
It's really ingenious. And the way they use product pseudo-randomness, that's just brilliant.
Yeah, it's like they found the perfect tool for the job, and it unlocks this whole new way of understanding the problem.
Exactly. And it wasn't just about brute forcing a solution. This paper is all about elegance and insight.
So what are the potential implications of this paper? Where do we go from here?
Well, I think this breakthrough on DHJ3, it could pave the way for understanding even longer combinatorial lines. We were just looking at lines of length 3, but what about 4 or 5 or even longer? Could this same approach be generalized?
It's like we've climbed one peak and now we see a whole range of mountains ahead of us.
I like that. And beyond the theoretical, this kind of pattern detection could have a big impact on things like cryptography, maybe even pattern recognition in artificial intelligence.
Okay, let's unpack that. How could this affect cryptography?
Well, think about designing encryption algorithms. Understanding how those patterns emerge could help us make them even stronger.
It's like knowing the enemy's playbook, so you can stay one step ahead.
That's fascinating. And what about pattern recognition? How does this tie in there?
Well, pattern recognition is all about finding meaning in complex data, right? Whether it's financial data, medical images, whatever. Understanding the math behind how patterns form could lead to better algorithms for recognizing those patterns. Wow, so we're not just proving theorems here. We're potentially revolutionizing how we approach real-world problems.
It's exciting stuff.
Absolutely. It just goes to show that math is more than just equations and proofs. It's about uncovering the hidden structures of the universe and using them to solve problems.
Well said.
This deep dive into DHJ3 has been a real eye-opener. It's a reminder that even in abstract math, there's beauty, there's elegance, and there's a whole lot of potential for real-world impact.
I couldn't agree more.
To all our listeners, keep exploring, keep questioning, and keep that mathematical fire burning bright. Until next time, happy deep diving. Hey there, ready for a deep dive into some serious math?
Absolutely.
Today we're tackling reasonable bounds for combinatorial lines of length 3.
Great paper.
We've got the paper right here, ready to unpack all the details.
Yeah, it's a gem for sure. It really dives deep into the density Hales-Jewett theorem.
VHJ.
VHJ for short. And makes some really, really significant strides.
Yeah.
Yeah.
For our listeners who might not have this specific theorem on speed dial, let's start with the basics.
Okay, sure.
What's the essence of DHJ, And why is the length 3 aspect so crucial in this paper?
So imagine you have a multidimensional cube, and each edge has k points.
Okay.
DHJK essentially asks, how dense does a subset of points within this cube need to be to guarantee you'll find a combinatorial line of length?
Okay.
And this paper tackles the case where k equals 3.
So we're searching for those lines that cut through the cube, hitting 3 points.
Right.
But this isn't just about any cube, right? We're dealing with higher dimensions here.
Exactly. And that's where things get tricky, right? As the dimensions of our cube grow, the number of possible points just explodes.
Right.
The challenge is to really pin down how dense our subset needs to be, even as the space becomes increasingly vast.
Now, this paper builds on some really serious mathematical heavyweights.
Oh, yeah.
Furstenberg and Katznelson's original proof using ergodic theory.
Right.
And then the Polymath Project's more recent elementary approach. Can you give us the historical context here? What were those breakthroughs and where does this paper fit in?
So Furstenberg and Katznelson's proof, that was groundbreaking. But it relied on some pretty sophisticated tools from ergodic theory.
Yep.
The Polymath Project, massive collaborative effort, provided an elementary proof, so, think simpler, more combinatorial tools, which was a huge step toward making DHJ more accessible.
Okay, so for DHJ3, did the Polymath Project nail down a specific density bound?
They did. They showed that any subset with density greater than a certain function of n being the dimension of the cube, would definitely contain a combinatorial line of length 3.
Okay.
The catch was this function involved a tower of exponents. Not the most practical thing to work with.
And that's where this paper swoops in with its reasonable bounds, right?
Precisely.
What's the breakthrough here?
This paper dramatically improves that bound, replaces that tower function with a function of finite height.
Wow.
Log n c, where c is a constant.
Okay.
It might still look complicated, but trust me, it's a massive leap forward in terms of practicality and the theoretical implications for related problems.
So they've essentially streamlined the criteria for determining whether a subset is dense enough to house those elusive combinatorial lines.
Exactly. And what's so fascinating is how this seemingly abstract problem, right, about cubes and lines, connects to some of the most famous theorems in number theory. We're talking van der Waerden's theorem, Semirates' theorem, the corners problem. This paper touches on them all.
Let's explore those connections, starting with van der Waerden's theorem, which I vaguely recall has something to do with arithmetic progressions and colors.
Oh, yeah, classic theorem.
Can you refresh our memory and explain how it links to DHJ?
Yeah, so van der Waerden's theorem states that if you color the positive integers with a finite number of colors, you're guaranteed to find arithmetic progressions, sequences where the difference between consecutive terms is constant of any desired length that are monochromatic.
Okay.
Meaning all the numbers in that progression have the same color.
Right, I remember that now. Something about no matter how you try to mix up those colors, you'll always find these neatly ordered progressions of the same color. But how does that relate to finding lines in a cube?
The connection might seem surprising, but it's actually quite elegant. Think of the points in our cube as representing numbers. Okay, we can encode the coordinates of each point as digits in a number system. In the case of DHJ3, it'd be a base 3 system. Now imagine a combinatorial line in the cube. The coordinates of the points along that line will form an arithmetic progression in our number system.
So the spatial arrangement of points in the cube translates into a numerical pattern of an arithmetic progression.
That's clever.
So where does Semirates' theorem fit into this picture? It also deals with arithmetic progressions, right?
It does. Semirates' theorem kind of strengthens van der Waerden's theorem. Instead of needing to color the entire set of positive integers, Semirates' theorem says if you have a sufficiently dense subset of the positive integers, you are guaranteed to find arithmetic progressions of any desired length within that subset.
So it's like focusing our search for patterns within a specific region of the number line.
But how does DHJ imply Semirates' theorem? It seems like they're talking about different things. Right, it all comes back to that encoding we talked about. If we encode the points in our cube as numbers, a combinatorial line in the cube directly translates into an arithmetic progression in our number system.
Okay.
So if DHJ guarantees the existence of a combinatorial line in a sufficiently dense subset of the cube, it also guarantees the existence of an arithmetic progression in the corresponding subset of numbers. That's the essence of how DHJ implies Semirates' theorem.
Okay, my brain is bending a bit, but I see the connection. These seemingly disparate areas of number theory are intertwined in surprising ways. Now, what about the corners problem? How does that tie into DHJ?
Right, so the corners problem is a little bit more visual. It asks, if you have a sufficiently dense subset of points in a grid, can you always find a right-angled triangle where all three corners are points in your subset? This might seem unrelated to DHJ at first glance, but the underlying logic, right, of finding specific configurations within dense sets is remarkably similar.
So are you saying that the techniques used to prove DHJ can be adapted to tackle problems like the corners problem?
Exactly, and it goes even further. The multidimensional Samorati theorem, which deals with finding even more complex patterns within dense subsets of higher dimensional grids, can also be linked back to DHJ. It's as if DHJ is a key that unlocks a whole network of interconnected problems in additive combinatorics.
All right, I'm convinced. DHJ is a mathematical powerhouse. But let's get into the nitty-gritty of this paper. How did they manage to achieve this improved bound? What's the magic behind the scenes?
Well, it's a really clever blend of inspiration from Shkredov's proof of the corners problem and the Polymath project's combinatorial approach to DHJK. They've taken these established techniques and added their own innovative twists.
Sounds like they're remixing mathematical masterpieces. What are some of the key ingredients in their approach?
One of the stars of their proof is this concept of product pseudorandomness.
Okay.
It's a way to rigorously analyze whether a function is truly random or if it has some hidden structure kind of lurking beneath the surface.
Okay, so we're dealing with functions now. How do those enter the picture?
All right, so remember, we're working with subsets of points in a cube. We can think of these subsets as being defined by functions that assign a value of 1 to points inside the subset and 0 to points outside.
Okay.
And analyzing these functions helps us understand the properties of the subsets themselves.
Got it. So this product, pseudorandomness, is a way to probe those functions, looking for signs of non-randomness.
Exactly. And it goes beyond simply checking if the function's values are evenly distributed. It involves analyzing how the function behaves when its inputs are restricted in specific ways, looking for correlations that would suggest some underlying structure.
So it's like a more sophisticated test for randomness, making sure those functions aren't trying to pull a fast one on us.
Precisely. And this leads to another key ingredient, inverse theorems.
Okay.
These are powerful tools that allow us to deduce information about a function's structure based on the types of correlations it exhibits.
Intriguing. So it's like having mathematical detectives who can examine those correlations and piece together a picture of the function's hidden secrets.
That's a great analogy. And the authors of this paper, they have two key inverse theorems that play a really crucial role in their proof.
Okay.
These theorems essentially say if you find certain types of correlations, then you know those functions aren't product pseudorandom.
So those correlations spill the beans, revealing that the functions are hiding some non-random structure.
Exactly. Armed with these inverse theorems, they then employ what's called a density increment strategy.
Okay.
It's a clever way to kind of iteratively zoom in on denser and denser subsets of our original cube, exploiting that lack of product pseudorandomness to push the density higher and higher.
I'm picturing this zooming in process, but can't this lead them into a mathematical dead end? What happens if they stumble upon a subset that's dense, but not well behaved in terms of product pseudorandomness?
That's where their final trick comes in, uniformization.
Okay.
It's like taking a messy room and organizing it. They've developed a technique to transform those unreleased subsets into ones that are product pseudorandom, all without losing too much density in the process.
So it's like they're ironing out the wrinkles, making those subsets smooth and manageable so they can continue their density increment strategy.
That's a great way to put it. And this whole process, analyzing correlations, applying inverse theorems, incrementing density, and uniformizing, eventually leads them to a point where the density becomes so high that it forces a contradiction. They essentially prove that their initial assumption of no combinatorial lines couldn't have been true in the first place.
It's a brilliant strategy, using those seemingly abstract mathematical tools to corner those elusive combinatorial lines. But I'm curious, for our listeners who are ready to roll up their sleeves and delve into the technical details, are there any particularly juicy bits of the proof you'd like to highlight?
Absolutely. The paper's packed with fascinating insights. And we're just getting started. Let's dive into some of the specifics.
Let's do it. Our listeners are eager for more.
One detail that stands out is how they handle the equal slices measure a concept used in the Polymath project's proof.
Refresh our memory. What's the gist of this equal slices idea, and how does this paper take a different approach?
So in the polymath proof, they imagine slicing the cube into sections, ensuring each slice contained roughly the same number of points from the subset they were analyzing. This helped them kind of understand how combinatorial lines were distributed across the cube.
I'm picturing those slices. So how does this paper deviate from that?
Instead of these equal slices, they work exclusively with product distributions. It's like analyzing each dimension of the cube independently and then cleverly combining those results.
So they're streamlining the analysis, finding a more elegant path through the mathematical jungle.
Exactly.
You also mentioned this intriguing term, disjoint product. What's that all about, and how does it connect to the corners problem?
Remember how we talked about those powerful inverse theorems that can deduce a function's structure based on correlations? Well, the disjoint product helps set the stage for those theorems to do their work. It's their way of translating the idea of combinatorial rectangles, those right-angled triangles we were looking for in the corners problem, into the language of DHJ3.
So they're building a bridge between these two seemingly different problems, using tools from one to solve the other.
Precisely. And this is where those two supporting lemmas, 6.1 and 6.2, come into play. They use the properties of disjoint products and product pseudorandomness to prove a crucial inequality that drives their density increment strategy.
Let's unpack those lemmas. Can you walk us through the logic of each one and how they contribute to the overall proof?
Sure. So let's start with lemma 6.1. Remember how product pseudorandomness is all about analyzing how functions behave when their inputs are restricted? This lemma uses that concept to establish a bound on a specific expectation related to the densities of sets E1 and E2. Think of it as putting a limit on how much those sets can deviate from being truly random.
So it's like making sure those sets aren't trying to sneak in any hidden correlations that would mess up the proof.
Exactly. Now, lemma 6.2 takes this a step further. It shows that a certain function, denoted as omega in the paper, concentrates around a specific value related to those densities. This means, though, in most cases, this omega function, which captures some intricate relationships between sets E1, E2, and S, behaves predictably.
So they're imposing some order on the potential chaos, showing that certain aspects of this problem are well-behaved despite the apparent randomness.
Precisely, and armed with these two lemmas, they can then tackle Theorem 4, the heart of their proof. It's here that they bring together all the pieces, the inverse theorems, the density increment strategy, the uniformization process to demonstrate that if a subset is sufficiently dense, it must contain those combinatorial lines.
All right, let's dive into Theorem 4. Can you break it down for us step by step?
At a high level, Theorem 4 uses the bounds from those lemmas along with a clever sequence of Cauchy-Schwarz inequalities.
Cauchy-Schwarz?
That
rings a bell.
To show that a specific correlation must be large if the set or subset of points does not contain a combinatorial line. Cauchy-Schwarz is a powerful tool in analysis often used to relate different expectations and derive inequalities. It's like a mathematical magnifying glass, allowing the authors to zoom in on specific correlations and expose the underlying structure.
So they're using this mathematical magnifying glass to essentially force a contradiction, showing that their initial assumption of no combinatorial lines can't hold true.
Exactly, and this leads them to their improved bound expressed in terms of that function of finite height we talked about earlier, a significant improvement over previous results.
I'm getting a sense of the elegance and power of their approach. It's like they've choreographed a complex mathematical dance with each step building upon the previous one to reach this beautiful conclusion.
That's a great way to put it, but before we get too carried away with the abstract beauty of it all, let's bring it back down to earth.
Yes, let's connect this back to the real world. What are the potential ripple effects of this work?
Well, remember those connections we discussed to van der Waarden's theorem, Semiraty's theorem, the corners problem, and even the multidimensional Semiraty theorem. Progress in understanding DHJ3 has the potential to impact all of those areas.
So it's like strengthening the foundation of a whole mathematical building, leading to more robust structures and perhaps even new architectural marvels.
Precisely, and beyond those direct mathematical connections. DHJ-type problems often have surprising applications in seemingly unrelated fields. Like, for instance, in computer science, similar concepts have been used to analyze the performance of algorithms, design efficient data structures, and even improve error-correcting codes.
Wow, so this isn't just some ivory tower math. it has the potential to influence the technologies we use every day.
Absolutely. And as we delve deeper into the world of higher dimensions with DHJK for larger K, we can expect even more unexpected applications to emerge. It's like exploring uncharted territory with the potential to discover new mathematical treasures that could reshape our understanding of the world.
I'm sensing a lot of excitement about the future of this field. What are some of the open questions or areas that you're particularly eager to see explored?
One of the most tantalizing questions is whether the techniques developed in this paper can be extended to higher dimensions. To tackle DHJK for larger values of K, the authors hint at this possibility, but the challenges are significant.
So it's like they've cracked open a door, revealing a glimpse of a vast and unexplored landscape. What are some of the obstacles that researchers might face as they venture into this new territory?
As the dimensions increase, the complexity of the problem explodes. The number of points grows exponentially, making it much harder to analyze the structure of subsets and the correlations between functions.
So it's like the mathematical jungle becomes even denser and more tangled.
Exactly. And the tools that worked so elegantly in lower dimensions might need to be refined or completely reimagined to handle the challenges of higher dimensions.
It sounds like a call to arms for mathematicians to push the boundaries of their creativity and ingenuity. Are there any other areas related to DHJ3 that you find particularly intriguing?
One area that's caught my attention is the connection to constraint satisfaction problems, or CSPs.
CSPs.
Yeah, the authors of this paper have a history of working in this area, and they've cleverly leveraged some of their previous results on CSPs to make progress on DHJ3.
CSPs, can you give us a quick primer on what those are and how they relate to this problem of finding combinatorial lines?
Sure. So CSPs are a broad class of problems where you have a set of variables and a set of constraints on those variables.
Right.
The goal is to find an assignment of values to the variables that satisfies all the constraints.
Okay.
Think of it like solving a complex puzzle where each piece has to fit just right.
Okay, I'm getting a visual, but how does that connect to DHJ3?
The authors have developed these powerful inverse theorems that apply specifically to a type of CSP called pairwise connected CSPs. These theorems allow them to deduce information about the structure of functions based on correlations, and they've found a way to adapt those theorems to the context of DHJ3, even though DHJ3 itself doesn't neatly fit into the category of pairwise connected CSPs.
So they're borrowing tools from one area of math and finding a way to apply them to another seemingly unrelated area.
Exactly. And this cross-pollination of ideas is one of the most exciting aspects of this work. It shows that seemingly disparate areas of math are often interconnected in surprising ways, and that exploring those connections can lead to breakthroughs in unexpected places.
It's a testament to the power of curiosity-driven research, following those intriguing threads wherever they might lead. It's like they've created a wormhole connecting different mathematical universes. But let's zoom back in on this paper's specifics. You mentioned earlier that they streamlined their approach by working with product distributions instead of the equal slices measure. Can you elaborate on how they achieved that simplification?
Sure. So in the Polymath project's proof, the equal slices measure played a crucial role in analyzing how those combinatorial lines were distributed, across those slices of the cube. This paper takes a more direct route by focusing on product distributions. Imagine you're looking at each dimension of the cube separately.
Oh.
A product distribution essentially treats each dimension as independent, analyzing the distribution of points along that single dimension.
Okay, so it's like breaking down a complex problem into smaller, more manageable chunks.
Exactly. And the beauty of this approach is it allows them to work with simpler tools throughout their arguments. They don't have to keep track of all those intricate relationships between different slices. They can just analyze each dimension on its own terms and then cleverly combine those results later on.
It's a reminder that sometimes taking a step back and simplifying the framework can lead to more elegant and efficient solutions. Now, you also mentioned this intriguing concept of a disjoint product, which seems to play a crucial role in bridging the gap between the corners problem and DHJ3. Can you unpack that a bit more?
Absolutely. The disjoint product is their way of capturing the essence of combinatorial rectangles, those right-angled triangles we were looking for in the corners problem, but in the context of DHJ3. It's a technical definition, but the intuition is that it allows them to establish conditions under which those powerful inverse theorems can be applied.
So it's like they're creating a mathematical dictionary translating concepts from one problem into the language of another.
That's a great way to think about it. They're finding a way to map the ideas and tools that worked for the corners problem onto the terrain of DHJ3. And this is where lemmas 6.1 and 6.2 enter the scene, providing the groundwork for Theorem 4, the heart of their proof.
Okay, let's revisit those lemmas. Can you remind us of their core logic and how they contribute to the overall strategy?
Yeah, so lemma 6.1 focuses on establishing a bound on a specific expectation involving the densities of sets E1 and E2. Think of it as setting a limit on how much these sets can deviate from being truly random. Remember our discussion about product pseudo-randomness? This lemma leverages that concept to ensure that these sets aren't sneaking in any hidden correlations that would mess up the proof.
So it's like a quality control check, making sure those sets are playing by the rules of product pseudo-randomness.
Exactly. Now, lemma 6.2 takes us a step further by focusing on a specific function, denoted as omega in the paper. This function captures some intricate relationships between sets E1, E2, and S, our target subset. The lemma demonstrates that this omega function concentrates around a specific value related to those densities. In essence, it shows that this function, despite its complexity, behaves predictably in most cases.
Okay, so they're taming the potential chaos, demonstrating that certain aspects of the problem are well-behaved despite the apparent randomness?
Precisely. And these two lemmas, 6.1 and 6.2, provide the foundation for tackling Theorem 4, the centerpiece of their proof. It's in Theorem 4 that they bring together all the threads. The inverse theorems, the density increment strategy, the uniformization process to demonstrate that a sufficiently dense subset must contain those combinatorial lines.
All right, let's break down Theorem 4 step by step. Can you walk us through the logical flow of their argument?
At a high level, they start by assuming that the set S, our subset of points, does not contain a combinatorial line.
Okay.
Then, using the bounds established in lemmas 6.1 and 6.2, along with some clever manipulations involving Cauchy-Schwarz inequalities, a powerful tool in analysis, they show that a specific correlation must be large.
Cauchy-Schwarz, that rings a bell. Can you remind us of its significance in this context?
It's essentially a mathematical magnifying glass, allowing them to zoom in on specific correlations and expose that underlying structure. By applying Cauchy-Schwarz strategically, they can relate different expectations and derive inequalities that reveal hidden relationships between those correlations.
So they're using this magnifying glass to essentially force a contradiction, showing that their initial assumption of no combinatorial lines cannot hold true.
Exactly. The large correlation they uncover contradicts their initial assumption, implying that the set S must indeed contain a combinatorial line if it's sufficiently dense. This leads them to their improved bound, expressed in terms of that function of finite height we discussed earlier, a significant improvement over previous results.
It's like they've set up a mathematical trap, carefully constructing their argument to corner those elusive combinatorial lines.
It's a beautiful example of how seemingly abstract mathematical tools can be combined in elegant and surprising ways to solve these complex problems. And it really highlights the power of collaboration and building upon previous work. They've drawn inspiration from Shkredov's proof of the corners problem and the Polymath Project's approach to DHJK, weaving those ideas together with their own innovations to achieve this breakthrough.
It's a reminder that progress in mathematics often involves standing on the shoulders of giants, taking those existing insights and pushing them further. But let's not get lost in the abstract beauty of it all. Can you bring this back down to earth for our listeners? Why should they care about these tighter bounds on DHJ3? What are the potential ripple effects of this work?
That's an important point. While the theorem itself might seem abstract, it has implications for various fields. Remember those connections we discussed to Van Borden's theorem, Semirates theorem, the corners problem, and even the multidimensional Semirates theorem.
Right.
Progress in understanding DHJ3 ripples outward, potentially leading to tighter bounds and new insights in those related areas as well.
So it's like strengthening the foundation of a whole mathematical building, making it more robust and potentially leading to new architectural marvels.
That's a fantastic analogy. And beyond those direct mathematical connections, DHJ-type problems often have surprising applications in seemingly unrelated fields. For example, in computer science, similar concepts have been used to analyze the performance of algorithms, design efficient data structures, and even improve error-correcting codes.
Wow, so this isn't just some ivory tower math. It has the potential to impact real-world technologies.
Absolutely. And as we delve deeper into the world of higher dimensions with DHEK for, larger K, we can expect even more unexpected applications to emerge. It's like exploring uncharted territory with the potential to discover new mathematical treasures that could reshape our understanding of the world.
It's a reminder that even the most abstract mathematical concepts can have profound and unexpected impacts on the world around us. Thank you so much for guiding us through this deep dive. It's been a truly illuminating exploration.
My pleasure. Always happy to share the joy of mathematical discovery.
And for our listeners, if you're feeling inspired to explore further, be sure to check out the show notes for links to all the resources we've mentioned. Until next time, keep those minds curious and those mathematical fires burning. Ready for some hardcore combinatorics?
Always.
Today we're diving deep into reasonable bounds for combinatorial lines of length 3.
Oh, this is a good one.
Yeah, this paper.
It
really gets into some fascinating problems.
It does. It really does. Way beyond just those lines.
Yeah.
We're talking Semiretti's theorem,
Right.
Horner's problem,
Yeah.
even touching on constraint satisfaction problems.
Oh, so.
The scope of this paper is impressive.
Before we go too far, though,
Sure.
we should probably start with the density Hales-Jewett theorem, right?
Absolutely. DHJ. It's kind of the foundation for everything we're going to be talking about.
Okay.
The DHJ theorem, at its core, is about finding guaranteed patterns and sets.
Okay.
Once they reach a certain density, think of our classic example. A Rubik's Cube. Each small cube is colored.
Okay.
Red, green, or blue.
Right.
A combinatorial line of length 3 is simply 3 cubes in a row, a column or a diagonal that are either all the same color or one of each.
Okay, so the DHJ is telling us how many of those little cubes need to be colored before we're absolutely guaranteed to find at least one of those lines.
Precisely.
No matter how we arrange the colors.
Yeah, exactly.
Yeah.
And the real challenge lies in finding the most efficient density requirement.
Right.
Previous work,
like
the polymath project, gave us a bound.
Okay.
But this paper significantly improves on that.
So the polymath proof gave us Guelph for a subset A3n.
Right.
To guarantee a combinatorial line of length 3.
Yeah.
Now, for those of us who aren't fluent in mathematical notation, can you break that down a little bit?
Yeah, so think of n as the dimension of our space.
Okay.
So for the Rubik's Cube, it would be like the number of small cubes along one edge.
Right.
So as n gets huge, that expression tells us what fraction of the cubes need to be colored to guarantee finding our line.
Okay.
The larger the n, the smaller the fraction.
Okay.
But it shrinks incredibly slowly.
And this paper manages to improve that.
Yeah.
They improve that shrinkage rate.
They do.
What's the new bound?
They've shown that a density of log is sufficient.
Okay.
It seems like a subtle difference.
Yeah.
But it's a massive improvement in terms of efficiency. As it grows, this new bound approaches 0 much faster.
That's really cool.
Yeah.
One of the things that I always find so fascinating is how these really abstract problems end up connecting to other areas of math.
Yeah.
And I remember reading that the DHJ has links to Semiretti's theorem.
Oh, it does, absolutely.
Maybe talk a little bit about that.
Yeah, so Semiretti's theorem deals with arithmetic progressions.
Okay.
So sequences where you add a constant to get the next term,
Right.
like 3, 7, 11, 15.
Got it.
Semiretti showed that any sufficiently dense set of integers must contain such progressions of a certain length. And the DHJ theorem can actually be used to prove Semiretti's result.
So the DHJ is almost like this sort of higher level principle.
Right, exactly.
Yeah, that can apply to both color patterns in our cube A and D to number sequences.
Exactly, a more general principle.
Okay.
And the connections don't stop there.
Oh, really?
The corners problem,
Okay.
which asks whether a dense enough grid of points must contain 3 forming a right isosceles triangle.
Okay.
Also ties back to the DHJ. It's like a master key.
Yeah.
Unlocking solutions across these different mathematical landscapes.
That makes you wonder what other connections are still out there waiting for us to find them.
Absolutely.
So let's shift gears a little bit and get into how this paper actually achieves this improved bound.
Okay.
And I know constraint satisfaction problems, or CSPs, play a role here.
They do, yeah.
Could you maybe give a quick rundown of CSPs for people who might not be familiar?
Sure, think of CSPs as complex puzzles.
Okay.
You've got variables, which can take on certain values, and constraints, which are rules about how those variables relate to each other. Sudoku is a classic CSP. You have to fill in numbers so that each row, column, and subgrid contains all digits from 1 to 9.
Right.
This paper uses sophisticated results from CSP theory to analyze the functions involved in the DHJ proof.
So they're using puzzle-solving logic to gain insights into a completely different area of mathematics.
Exactly. Yeah, it's really fascinating.
It is. It's really cool.
It really is a testament to the interconnectedness of these seemingly disparate mathematical fields.
Right.
And by leveraging these CSP tools, the authors gain a deeper understanding of the structures at play in the DHJ theorem, ultimately leading to their improved bounds.
I'm starting to see how this paper brings together so many different threads.
Yeah.
We've got the DHJ at the foundation. We have these links to Semeretti and the corners problem.
Right.
And now this unexpected connection to CSPs.
It is pretty impressive, yeah.
It really is. And there's even more.
Oh, there is.
The authors borrow a clever technique from Skridov's work on the corners problem.
Okay.
Involving something called a disjoint product.
It's a way to combine sets with specific properties, and it turns out to be crucial for their approach to the DHJ.
Disjoint product.
Yeah.
Can you tell me a little more about how that works and why it's so important?
So in essence, the disjoint product lets us build new sets from existing ones.
Okay.
In a way that preserves certain properties. In the context of the DHJ, these disjoint products act as a kind of proxy for combinatorial rectangles, which are key structures in the proof.
So they're using this technique to kind of create these building blocks that mimic these combinatorial rectangles.
Precisely.
Okay.
But to ensure this analogy holds up, we need to make sure these disjoint products are well behaved.
Right.
And that's where product pseudorandomness comes in.
Okay.
Yeah.
Product pseudorandomness.
Oh, it's a mouthful.
Yeah, it's a big one.
Yeah.
Can you break that down?
Yeah, so imagine you have a function that takes some input and produces an output. If this function is product pseudorandom, it means it behaves almost as if it were generating truly random outputs. Even when you look at specific parts of its behavior, it's kind of like a master of disguise.
Right.
Mimicking randomness with incredible accuracy.
So why is this so important in the context of the DHJ proof?
Because it ensures that our disjoint products, those stand-ins for combinatorial rectangles, actually behave the way we need them to.
Okay.
If they weren't pseudorandom, the whole analogy could fall apart. Got it? The proof wouldn't work.
So product pseudorandomness is kind of like a quality control check.
Exactly.
All right, so what comes next?
Now we bring in the big guns. Inverse theorems for CSPs.
Oh, okay.
These theorems are like powerful detective tools that allow us to deduce the internal structure of a function based on its observed behavior.
So we can kind of reverse engineer the blueprints of these mathematical functions just based on what they're doing.
Precisely.
Yeah.
That's incredible.
It is. It's really powerful.
Yeah, and the specific inverse theorems used in this paper are particularly potent, dealing with functions over 3 Ainary and 4 Airy distributions, meaning they operate on sets of 3 or 4 variables.
This is where things start to get really complicated. Yeah. What happens next?
So the paper explores different ways to measure or count those combinatorial lines.
Okay.
It might seem like a technical detail, but it's crucial for their approach.
Why is that so important?
It turns out that choosing the right measure or mathematical yardstick can make a huge difference in the effectiveness of the proof.
Okay.
Think of it this way. You wouldn't use a ruler to measure the volume of a liquid, you'd use a measuring cup.
Right.
Similarly, in this case, they need a measure that's specifically tailored to the properties of those combinatorial lines and how they interact within these dense sets.
So it's about finding the right tool for the job.
Exactly.
And I imagine this choice of measure plays a big role in their ability to establish those lower bounds.
Absolutely.
For the number of lines.
Yeah. By carefully selecting this customized measure, they gain a level of control and precision that wouldn't be possible with a more generic approach.
Okay.
It allows them to make very specific statements about the behavior of those combinatorial lines, even within extremely dense sets.
This is all very impressive. But what are the implications of this work? What does this improved bound for the DHJ3 theorem mean for other areas of math?
That's a great question. Remember how we talked about how the DHJ theorem is linked to Semiretti's theorem about arithmetic progressions?
Yes.
Well, this improved bound potentially strengthens that connection. It could lead to more efficient ways to find those progressions in number sequences, which has implications for areas like cryptography and coding theory.
So it's like tightening a bolt in the foundation of a building.
Precisely.
And that ripple effect strengthens the entire structure.
Exactly.
Awesome.
And the connections don't stop there. Remember the corners problem we discussed? Finding those right isosceles triangles in a grid of points. This paper could shed new light on that problem as well, potentially leading to new insights and more efficient algorithms for solving it.
Wow, it's incredible how such an abstract problem can have consequences across all these different areas of math.
It's a beautiful example of how mathematical ideas can travel across seemingly disparate fields, sparking new discoveries and pushing the boundaries of knowledge. And I wouldn't be surprised if this paper leads to even more unexpected connections down the line.
Well, I'm feeling a little overwhelmed by the sheer depth and scope of this work.
I can understand that, yeah.
And we've only just scratched the surface. I think we need a break here, and then we'll come back and we can delve even deeper into the intricacies of this proof.
Sounds good. All right, so let's jump back into the core of this paper.
Oh.
Remember we left off talking about the density increment approach.
Right, like that mathematical seek and you shall find.
Exactly, but with a lot more strategy involved.
So how do they actually implement this density increment argument?
Well, that's where all those tools we discussed come in.
Okay.
The inverse theorems for CSPs let them analyze the structure of functions that represent patterns in these dense regions.
Okay.
And they use these insights to show that if a region doesn't have enough combinatorial lines, there must be an even denser subregion where those lines are more likely to appear.
So it's like we're playing this mathematical hide and seek.
Yeah.
And the inverse theorems are like our heat-seeking device.
Exactly, guiding us towards those hidden lines.
I like that.
And to make sure this heat-seeking process works smoothly,
Yeah.
we need those disjoint product sets to behave predictably.
Right.
That's where product pseudo-randomness comes in.
Okay.
By requiring these sets to have this almost random property, they can make really reliable calculations about their measures and how they overlap.
Okay.
Even as they zoom in on smaller and smaller regions.
So it's like having a guarantee that your measuring tools are accurate, even at incredibly fine scales. I'm seeing how all these pieces are fitting together now.
Yeah, it's like building a complex machine.
Yeah.
Where each component needs to be precisely engineered to ensure the whole thing runs flawlessly.
Right. And the authors have done a really remarkable job putting all this together.
They have, yeah.
Now, I remember you mentioning that they also explore different ways to measure or count those combinatorial lines.
Yes.
Can you talk a little bit more about why that's necessary?
Sure. So it turns out that choosing the right measure, or mathematical yardstick, can make a huge difference in the effectiveness of the proof.
Okay.
Think of it this way. You wouldn't use a ruler to measure the volume of a liquid, you'd use a measuring cup, right?
Right.
Similarly, in this case, they need a measure that's specifically tailored to the properties of those combinatorial lines and how they interact within these dense sets.
So they had to find the perfect tool for the job.
Exactly.
Okay, so this choice of measure really affects their ability to establish those lower bounds for the number of lines.
Absolutely. It gives them a level of control and precision that wouldn't be possible with a more generic approach.
Okay.
It lets them make really specific statements about the behavior of those combinatorial lines, even within extremely dense sets.
That's fascinating.
Yeah.
Now, all of this is incredibly impressive, but what are the bigger implications here?
Yeah.
What does this improved bound for the DHJ3 theorem mean for other areas of math?
Right. Well, remember how we talked about the connection between the DHJ theorem and Semiretti's theorem about arithmetic progressions? Well, this improved bound potentially strengthens that connection.
Okay.
It could lead to more efficient ways to find those progressions in number sequences, which has implications for areas like cryptography and coding theory.
So it's like they've made the connection between these areas even stronger.
Exactly.
And that could lead to new discoveries in those fields.
Precisely.
Okay, very cool.
And the connections don't stop there.
Oh, really?
Remember the corners problem we discussed?
Yeah, finding those triangles in a grid of points.
Right. Finding those right isosceles triangles. This paper could help us understand that problem better, too.
Okay.
It could lead to new insights and more efficient algorithms.
That's amazing to me, that a problem about colored cubes can have such far-reaching consequences.
It really is.
It really speaks to how connected math is.
Yeah, it's a beautiful example of how mathematical ideas can travel across seemingly disparate fields, sparking new discoveries and pushing the boundaries of knowledge.
I'm starting to feel a little overwhelmed again by how deep this all goes.
It's a lot to take in, yeah.
We've only just scratched the surface.
We have.
I think we need another break to let all this sink in.
Okay.
And then we can come back and finish up our deep dive into this paper.
Sounds good. All right, let's wrap things up with this paper.
Yeah, it's been quite a journey.
It has.
Exploring this density Hales-Jewett theorem.
Yeah, we've gone pretty deep.
And all these fascinating problems that are connected to it.
Absolutely. It's remarkable how the authors combined those existing techniques.
Yeah.
Like Shkredoff's disjoint product.
Right.
With these new concepts like product pseudorandomness.
Right.
To really make a breakthrough in our understanding of the DHJ3 theorem.
Yeah, they've really set a high bar with this work.
They have.
Not just for the ingenuity, but also just the level of detail in their analysis.
For sure.
But beyond all the technical brilliance,
yeah,
I keep thinking about those connections to Semirates' theorem and the corners problem.
Absolutely. It's like they've strengthened the links between those different areas of math.
Right. And it just highlights how progress in one area can lead to all these unexpected discoveries in other fields.
Exactly. And I think this paper could lead to a lot of new research in those connected areas. For instance, the improved bound for the DHJ3 theorem might inspire mathematicians to take another look at Semirates' theorem.
Okay.
Looking for even more efficient ways to find those arithmetic progressions in number sequences.
Which has implications for...
yeah, exactly. Has those implications for cryptography and coding theory.
Right.
Where those patterns in data are so important.
So it's like they've given us this new, more powerful tool.
Yeah, a new lens.
To look at these problems with. And potentially find new solutions.
Absolutely. And the same goes for the corners problem.
Right, with finding those triangles.
Yeah, those, isosceles triangles and grids.
Right.
Their work could inspire completely new approaches.
Okay.
Leading to faster algorithms and a better understanding of those underlying structures.
It never ceases to amaze me how a problem that seems so abstract, like colored cubes,
I know, right,
can have consequences across so many different areas of math.
It's incredible. It really speaks to the interconnectedness of mathematical ideas.
It does.
And it shows how important it is to keep exploring even those abstract problems.
Right.
Because you never know what breakthroughs they might lead to.
Absolutely. Now, before we go, I have one last question. We've talked a lot about how the authors have improved the bounds for the DHJ3 theorem. But is there a limit to how much those bounds can be improved?
That's a great question.
Yeah, could there be an even tighter bound out there just waiting for us to find it?
That's something mathematicians will definitely keep working on.
Okay.
This paper is a huge step forward, but it's probably not the end of the story. Mathematicians love to find the best possible bounds.
Right.
And I'm sure this work will inspire a lot more exploration.
So it's like they've climbed one mountain.
Yeah.
But there might be an even taller one out there.
Exactly.
That's a good analogy.
It really captures that spirit of mathematical inquiry.
Yeah.
Every answer just leads to more questions.
Right.
And every breakthrough opens up new possibilities.
That's a great way to put it.
This paper has definitely pushed the boundaries of what we know.
It has.
But the journey is far from over.
Well, I'm excited to see where it goes from here.
Me too.
And it's been fantastic talking about this with you.
Likewise, it's always fun to discuss such elegant math.
Yeah, absolutely. This was a good one.
And remember, whether you're a seasoned mathematician or just starting out, there's always more to discover.
Right.
So keep exploring, keep questioning, and keep diving deep.
Couldn't have said it better myself. And on that note, we'll wrap up this episode of The Deep Dive. We hope you've enjoyed our exploration of reasonable bounds for combinatorial lines of length 3. Until next time, keep those mathematical minds engaged.